session on commitments. We're gonna have three talks. The first talk is by maybe the speaker can talk. You know where to get your. So the first talk is gonna be by Hong Xiao Wang, Xiu Ming Yu, Yamin Zhao, Zhou Jiang. The speaker is Hong Xiao. The name of the paper is Aggregatable Succinct Material Vector Commitment for Lattice, and you can start.
Yeah, thank you for the introduction. I'm Hong Xiao Wang from the University of Hong Kong. I'm going to introduce our works, which is updatable, aggregatable, succinct macro vector commitment from lattice. First, let's review the notion of the vector commitment, which one can commit a vector X to a commitment C, and the commitment C can be opened to to the value xi at index I with the opening pi I, and the pi I can be verified by others. But for macro vector commitment, it becomes a little different. One have to decide whether he will commit to vector X or not. If he does commit to vector X, he need to run hcom to get hard commitment C, which there is a vector inside. Otherwise, he can run scom to get a soft commitment C prime, where there is no message inside. For the commitment C, it can be both H open and S open to the specific value xi and at the index I with the hard opening pi I or the soft opening tau I, which can be H verified and S verified separately. And for the soft commitment C prime, it can only be S open to any value X at the index I with the soft opening tau I, and tau I can be only S verified. In more details, in hcom, it takes the common reference string CRS and vector X as input, and it outputs soft commitment C and the auxiliary information UX. And in hopen, it takes AUX and index I as open and outputs hard opening pi I. And in verify, it will check whether pi I is valid. And for as open for the hard commitment, in as open, it takes the AUX a flag H, which indicates that it's for the hard commitment, and the value xi and index I as input, and output soft opening tau I. And as verified, it will check whether tau I is valid. There is a notion named proper MVC, which is for all known constructors. The soft opening tau I is a proper subset of the hard opening pi I to the same message, so as the S verify and H verify. And in scom, it only takes CRS as input and output soft commitment with the auxiliary information. And to S open for the soft commitment, it takes AUX and a flag S, which means it's for the soft commitment, and value X and index I as input, and output soft opening tau I. And as verify, it will check whether tau I is valid. The macro heading is the secure requirement for the macro vector commitment, which is for any efficient adversaries. It cannot distinguish between hard commitment C and soft commitment C prime, even with their soft openings. To analyze the macro heading, we first define the simulating algorithms, which one can run fcom to get a fake commitment C, where there is no message inside. This is very similar to the soft commitment, but the fake commitment C can be both EH open and ES open to the any value X at the index I with the hard equivocation pi I and soft equivocation tau I. In more details, in both EH open and ES open, it have to take the triple key TK as input, and it outputs a hard equivocation pi and soft equivocation tau. We use a equivocation game for proper MVC to analyze to prove the macro heading. For the adversaries, it cannot distinguish between the hard commitment and fake commitment, even with hard openings and hard equivocation. And also, the adversary cannot distinguish the soft commitment and fake commitment, even with their soft opening and soft equivocation. And that can help us to prove the indistinguish between the hard commitment and soft commitment with their soft openings. And there is another security requirement, which is macro bounding, which is for any efficient adversaries cannot open a hard commitment C to two different values at the same index successfully. For any non-trivial macro vector commitment, it have to satisfy the successiveness, which is for all commitment and openings. It should be short, which is usually polynomial with the log of the length of the vector x. And here we give a summary for the state of the art of the macro vector commitment. There are two schemes based on non-core post-component assumption, which can support update or aggregate. And there are only one constructions for the post-quantum assumptions, which is SAS assumptions, use the generic frameworks with the lattice-based components, but it cannot support update and aggregate and have a large auxiliary information. And in this work, we give two schemes, which one is based on cis assumptions and can support update, and the other one is based on basis assumptions, which is a new flexible family of basis agreemented cis assumptions proposed by V and Wu in Eurocrypt 23. And it can support update and aggregate and have a smaller auxiliary information. For the generic work, we talk more details. It's including a standard macro commitment and a standard vector commitment. First is generate L macro commitment of each entries of the vector with auxiliary information. And second, it generates a vector commitment sigma to the vector of the macro commitment with another auxiliary information. And then it publish sigma as the vector macro vector commitment and store all the auxiliary information. And to generate an opening, it first open the vector commitment sigma at index I and open the macro commitment Ci. To verify, it first verify the vector commitment and then verify the macro commitment. Due to the generic framework, it cannot support update and aggregate easily because it's decided by its components. In this work, we give a non-black box construction of macro vector commitment based on basis frameworks, and we give two institutions. One is based on basis structure with smaller auxiliary information and can support update and aggregate. And the other one is based on cis assumptions, support update. And we also redefine the property of update in macro vector commitment, it can support update to both soft commitment and hard commitment. And we introduce some new properties, which is stateless update, differential update, and updatable macro heading. And we show application on zero knowledge set and zero knowledge elementary database, which is we can use our macro vector commitment to build a lattice space updatable L arrays ZKS and ZKEDB with batch verification. And in this talk, we only talk the high level view of the non-black box macro vector commitment based on basis frameworks. As a start point, we begin with the basis vector commitment. In their CRS, there are two matrices. One is BL, which is composed of L A1 to AL matrix and L gadget matrix, and its triple T of the matrix BL. It is secured because is under the basis assumption. Even published the triple of BL is secured. And in their commitment relation, the commitment C equals xi times E1, which is a basis vector, and plus matrix AI times VI, which is short openings. And the trade-offs in CRS allows for joint sampling of commitment C and all openings A1 to AL by sample query algorithms with the trade-off BL. We want to emphasize that the basis vector commitment supports advanced property which names the proper opening, which is the commitment C is statistically close to uniform over ZQ, and for all openings, is statistically close to the distribution of the pre-image of the C minus XI1 under the matrix AI. And we show the extension to basis frameworks with our two observations for the basis vector from commitment. For the observation 1, which is the private openings, implies that there exists simulating algorithms that can generate a fake commitment C prime without any message. And it can also generate its equivocation openings VI prime to any value xi with only with the trade-offs of the AI. And the distribution of them is statistically close to the real one. And for the other observation, if we extend BL to BL prime with any matrix D1 to DL, the trade-off T prime of BL prime can be naturally extended by pending the zero at the suitable position. And the properties of correctness, bounding, and private openings still hold under the basis assumption. And here we give our approach on macro vector commitment. We add D1 to DL as the commitment and revise the commitment relation. And we give how to generate the matrix D in different commitment. In hard commitment, we let DL equals AI times RI, and the openings VI can be joint sampled by the sample query algorithm with the trade-off T prime, which is similar to the basis vector commitment. And for the soft commitment, we let DL equals gadget matrix G minus AI times RI prime, and the opening VI can be sampled by sample query with RI prime. Since RI and RI prime are randomly sampled over base, and the DI is indistinguished in hard commitment and soft commitment, and the soft opening VI from both hard and soft commitment is statistically close to the distributions of the pre-image, and RI adds additional part in hard openings to check whether DI equals RI times RI in hard commitment. They seems all good, but there left a problem, which is the size of D1 to DL is linear with the loss of the input. So to solve the problem, we give the decision on basic structure. In basic structure assumption, A1 to AL are structured by the WI matrix times A, where WI is a public random invertible matrix, and and A is sampled randomly. So R1 to RL can be structured by DL times D hat, where D hat equals AR or equals G minus AR. It depends on the hard commitment and or soft commitment, where R is randomly sampled over base. And therefore, the commitment can be comprised to C and D hat. However, we give the decision on these assumptions, unlike basic structure assumption. A1 to L in this assumption are randomly sampled independently. So D1 to DL are independent as well. We solve the problem using a standard vector commitment. We commit D1 to DL to sigma and then publish C and sigma instead of D1 to DL. Although this method can cause the same size of the auxiliary information as the generic frameworks, we want to emphasize that it can support updates due to its non-black box construction. As a summary, this work focuses on the non-black box macro vector commitment based on basic frameworks, and we give two institutions. One is can retrieve smaller auxiliary information and support update and aggregate, and the other is based on standard assumptions that can support update. And for other parts, please see our papers for more details. So thank you. I'm happy to answer questions from the audience.
The question? We actually have time.
Yeah, so in the reboot paper, they have this, they get functional commitments using some kind of homomorphic.
Yep.
Thing.
Yep.
So can we use that here to get some kind of?
Yeah, our techniques may help in the function commitment, but it needs to find suitable application, it maybe have no meanings with the, how to say, macro function. Yeah.
Question? We actually have time. Thanks again, our speaker. So it's going to be by Benoit Libert. The name of the talk is Simulation Extractable KCG Polynomial Commitment in Application to Hyperplot. And Benoit is going to give the talk.
We can switch to full screen mode.
Wait, I think I saw that the maybe because I think it was a phone that with not find it.
Sorry, yeah.
Here, present is this one. Perfect. Okay. And we need to use this.
Okay.
So
Thanks for the introduction. So I'm going to tell you about simulation extractable polynomial commitments and snarks. Snark is a succinct non-interactive argument of knowledge. It's a short proof sent by a prover to a verifier about some NP statement. Succinctness means that the size of the proof should be much smaller than the size of the circuit that describes the relation, and it should also be smaller than the witness. In terms of security, SNARK should be knowledge sound, meaning that a convincing prover must know a witness that satisfies the relation. And zero knowledge means that a proof should leak nothing about the witness beyond the fact that it satisfies the relation. There is a general method of building a SNARK, which is to combine a polynomial interactive oracle proof with a polynomial commitment. Polynomial IOP is a multi-round extension of PCPs. In each round, the prover sends oracles to a verifier. Each oracle is a polynomial, and the verifier can obtain an evaluation of these polynomials and make a decision based on this. When the PIOP is turned into a SNARK, then each oracle to a polynomial is replaced by a commitment to this polynomial. And each polynomial evaluation should come with an evaluation proof that should be of size much smaller than the degree and the verification cost as well. It was shown that if a polynomial commitment is a simulation, is knowledge sound, and if the polynomial IOP is a negligible knowledge error, then the SNARK is knowledge sound. Knowledge soundness means that if a convincing prover can create a valid proof, then there is an extractor that can reconstruct a witness using oracle access to the prover, either by rewinding the prover or using a non-black box access to the prover. In some applications, knowledge soundness is not sufficient because it does not guarantee anything against an adversary that can observe proofs generated by honest users and try to mold them in some way to create a proof for a related statement for which it does not know a witness. So to prevent this kind of attack, we need the notion of simulation extractability, which means that knowledge soundness should be preserved even when the adversary can observe proofs by honest users and even simulated proofs by a zero knowledge simulator. Formally, there is an experiment between a challenger and an adversary. In the beginning of the experiment, the challenger generates a CRS and a simulation trapdoor. The CRS is given to the adversary. The adversary can make a number of simulation queries. The adversary in each query chooses a statement that may be a true statement or not, and obtain a simulated proof for this statement. And then they keep going like that for a number of queries. And then the adversary outputs a statement X star and a proof pi star. And the adversary wins if pi star verify for X star. And yet the knowledge extractor fails to obtain a witness. And of course, the statement X star and the proof pi star should not have been obtained by trivially recycling an input and an output of the simulator. This is the way simulation extractability is formalized. There are quite a few results on simulation extractable SNARKs. For example, modification of the Growth 16 SNARK was shown simulation extractable in DHGM. Planck, Sonic, and Marlin were also shown simulation extractable in DHGM and the random oracle model. The same holds for bulletproofs and Spartan, but only in the random oracle model without DHGM. These results were for specific schemes. There are also compilers that work for general compilers that give simulation extractability with black box straight line extractors, but they tend to be less efficient. And there are more efficient compilers that apply to SNARKs that are already deployed in the industry. For example, at the last TCC, there were two papers. One of them by Kolvais et al., who showed that if an argument system has a trapdoor-less simulator and weak unique responses, then it's simulation extractable. A trapdoor-less simulator is a simulator that does not use the trapdoor of the CRS, but only programs the random markers. And in the same conference, there was another paper by Faonio et al., who showed that you can also obtain simulation extractability if you use a polynomial commitment that satisfies a weak notion of simulation extractability, even if it's a trapdoor-based simulator. These two compilers are only, at least in their initial description, they are only known to apply to univariate polynomial IOPs. and they are not known to extend to multilinear ones. In the paper, our motivation is to construct a simulation extractable snark from a multilinear polynomial IOP because they make it easier to obtain a linear time prover. So to do this, we construct a strongly simulation extractable PCS in the AGM and random oracle model with a simple top-doorless simulator. And we use it to obtain a simulation extractable instantiation of hyperplonk. So we don't give a general compiler. We just do it for one multilinear PIOP, but we believe it can be applied to other candidates. So the main result of the paper is to give a simple method of constructing strongly simulation extractable PCS schemes from KZG-based constructions. We give two constructions. One of them is for multivariate polynomials. It's based on a randomized version of PST commitments that was published in an ePrint paper some years ago. For this construction, we obtain almost the same efficiency as the original scheme. The size of evaluation proofs is only longer by one field element, and the verification time is the same. In the univariate case, we give a more efficient construction, which is a randomized version of KZG. And if you compare it with the initial randomized KZG, the size of evaluation proofs is only longer by one scalar. And then we apply the multivariate construction to hyperplonk to make it simulation extractable while preserving the linear time prover and the support for a large degree custom gates. So in the next few slides, I will give a quick reminder on KZG commitments and multivariate extensions of KZG. And I will explain how to make them simulation extractable. I will give some intuition as to why it's simulation extractable. And I will explain in the last section how to apply it to hyperplonk. There was already a talk on KZG this morning, but a quick reminder is that KZG has a structured setup. There is a bunch of monomials in the exponent. And when you want to commit to a polynomial, you compute an evaluation of this polynomial in the exponent for the input alpha, which you can do using the monomials in the exponent. To prove that a polynomial evaluates to the output y for the input z, the prover can prove that this is true if and only if there exists a quotient polynomial that satisfies this identity. Then an evaluation proof can just be a commitment to the quotient polynomial, and it can be verified using a pairing because you can compute a product of polynomials in the exponent and check that this identity is satisfied, this equality holds when the variable takes on the value alpha. It's evaluation binding under the strong Diffie-Hellman assumption. It's also knowledge sound in the algebraic group model, but it's malleable. But yet, even though it's malleable, it still satisfies a weak notion of simulation extractability, which can be sufficient to build a snark, as shown by Faonio et al. At TCC last year. There is a multivariate extension of KZG that was proposed by Papamontu et al. At TCC 10 years ago. If you want to commit to a polynomial with mu variables, you need a CRS that contains not only one trapdoor, but mu trapdoors. And also in the CRS, you need encodings of all possible monomials in the exponent. And then when you want to commit to a polynomial, you can do exactly the same thing as in the univariate case. In the univariate case, you compute an evaluation of this polynomial in the exponent for an input consisting of the trapdoor of the CRS. Then when you want to generate an evaluation proof, you can use the fact that evaluates to y for an input consisting of z1 until z mu, if and only if there exists a set of quotient polynomials that satisfy this identity. And then again, an evaluation proof can be a set of commitments to the quotient polynomials, which can be verified using a pairing to compute polynomial products. You can verify that this identity is satisfied, this equality is satisfied when the variables take on values that are the trapdoor of the CRS. The commitment is not hiding because it's deterministic, but there is a simple way to make it hiding. It was done in a paper by Zhang et al. A few years ago. The idea is to randomize all commitments as Petersen commitments. There is an additional secret element in the CRS, which is used to randomize all commitments. When you want to compute a commitment to a polynomial, compute a Petersen commitment to the evaluation of this polynomial for the input alpha 1 until alpha mu. And then in each evaluation proof, the commitments to the quotient polynomials is randomized exactly in the same way. The difference with the deterministic case is that there is an additional component in each evaluation proof, an additional element pi r, which is used to cancel the effect of randomizations in the verification equation. And with this modification, you can prove that the construction is hiding, and the evaluation proof is zero knowledge. It's also knowledge sound in the algebraic group model under a parameterized D-log assumption. There is a proof in the paper, but it's malleable. Yet, even though it's malleable, we can easily make it simulation extractable, as we show in the paper. To make it simulation extractable, we don't change the CRS. We don't change the commitment either. We just change the generation of evaluation proofs. To prove an evaluation, we first compute the first mu elements of the evaluation proof as before, as commitments to the quotient polynomials. The difference is that instead of revealing the last element pi r, we generate a proof of knowledge of this element using a sigma protocol, and we make it non-interactive using the Fiat-Shamir heuristic. To achieve non-malleability, we need to include all those, the first mu elements of the evaluation proof in the input of the Fiat-Shamir hash function to prevent the adversary from randomizing them. And also we need to include the Shamir hash function. The label contains metadata that should be attached to the proof in a non-malleable way. Typically in the snark, it contains all earlier message of the prover that the adversary should not be able to tamper with. This modification, we can prove that the construction is simulation extractable in the DHG random oracle model under a Q-type discrete log assumption, which says that alpha is infeasible to compute, even if you have d times mu powers of alpha in the exponent in both groups. The extractor does not have to rewind in the proof. And the idea of the proof is that essentially, in the verification equation, the verifier computes a product of pairings that depends on the components of the proof and the commitment. And this element R pi is hashed in the Fiat-Shamir hash function, and the result is compared with Fiat-Shamir challenge content in the evaluation proof. And since we are in the random oracle model, the adversary must have made a hash query on this element R pi. And since we are also in the algebraic group model, the adversary must have supplied an algebraic representation of this R pi that allows writing R pi like this for some polynomial R with mu plus one variables. And this polynomial is given to the reduction as part of the algebraic representation. Then the reduction can also use the algebraic representation of the commitment and the evaluation proof components to construct another polynomial T with mu plus one variables that vanishes on input of the trapdoor of the CRS. And using a statistical argument, we can show that this polynomial is not identically zero with high probability unless the algebraic representation of the commitment is actually a witness. So we can show that either the reduction obtains a witness or it obtains a polynomial which is non-zero that vanishes on input of the trapdoor of the CRS. And in turn, this polynomial implies a univariate polynomial that contains alpha as a root. But this is the idea of the proof, and to make it, to prove that the adversary cannot recycle an output of the simulation as part of its forgery, we have to, actually we can use the non-malleability of Fiat-Shamir by distinguishing a few cases in the proof. This concludes the description of the commitment. Now let me tell you briefly how we can apply it to hyperplank. Hyperplank is a linear time prover snark, which is essentially Planck over the Boolean hypercube. The idea is that the prover encodes the computation trace in the columns of a matrix that contains the left input, the right input, and the output of each gate. Then the prover commits to witness polynomials that are multilinear polynomials that evaluate to the columns of M over the hypercube. Then these witness polynomials are shown to satisfy two conditions. The first one is a gate identity that shows that all gates are evaluated properly. The second condition is a wiring identity, which shows that the evaluation trace is consistent with the wiring of the circuit. This is done by showing that the witness polynomials satisfy these equalities everywhere on the hypercube for some permutation sigma that encodes the wiring of the circuit. So this is the high-level idea, and to make it simulation extractable, we need to build a trapdoor-less simulator, which works in the following way. The simulator computes a fake witness polynomial that satisfies the gate identity, but not the wiring identity. And this is doable by computing the multilinear extension of some polynomial. So we can easily generate a proof for the gate identity because we know a witness for it, but we cannot do it for the wiring identity. But we can still simulate a proof for the wiring identity by simulating a proof for some polynomial evaluation. We can use the trapdoor-less simulator of the PCS to simulate a proof that some polynomial evaluates to 1 on a specific point of the hypercube. To achieve non-malleability, we also need to include all early messages in the protocol in the label of each PCS evaluation proof. And this is why we introduced labels in the evaluation proofs. To summarize, we gave two constructions of simulation extractable PCS that satisfy a strong notion of simulation extractability in DGM and random oracle models. And they are almost as efficient schemes as the malleable schemes they start from. And we give, in both of them, we give a simple trapdoor-less simulator that comes from the Sigma protocol and the Fiat-Shamir heuristic. And we obtain, as a simulation extractable instantiation of hyperplonk, which is not optimized as described in the paper, but it can be optimized by using all multivariate polynomials, and even using zero mode or Gemini to reduce the number of pairings to a constant, the cost of increasing the cost of the prover. And this is it.
So my question would be, could you use some matching technique for the Sigma protocol to, to improve either so that you don't have to do one Sigma protocol for each KZG proof, but kind of batch them together?
Actually, yes, if you linearize all multivariate commitments, you can use the batch evaluation protocol Hyperplonk, and eventually you only need one evaluation of a multivariate PCS.
Okay. So, so instead of, it's just because the protocol unlocks one single evaluation.
Yes, there must be evaluation protocol as they describe it in the paper.
Let's take the speaker again. He's going to give answer the next talk, so he's going to get a lot of flows today. So the next talk is vector commitment with proofs of smallness, short range proofs, and more. Benoit is going to give the talk.
Yes.
Okay, present. Okay, perfect. So I'm going to tell you about vector commitments with short proofs of smallness, which means that there is an efficient way to generate a short proof that the committed vector is small. So I will first give a quick overview of vector commitments, the applications, and the prior work. Then I will explain how we can build proofs of smallness using as a building block a short proof that the committed vector is binary. Then I will give two applications. One of them is a very short range proof, and the second one is a short proof that ring delivery ciphertext is a valid ciphertext. In a vector commitment, the committer is a vector of ring elements and can generate a short commitment to it in such a way that later on it can succinctly open the commitment for one position of the vector by revealing a short opening. The size of the opening should be at most polylogarithmic in the dimension, and the size of the commitment as well. The motivation was initially in zero-knowledge databases with short proofs, but they found applications later on in verifiable data streaming, authenticated dictionaries, cryptocurrencies, and many more. There is a folklore construction of vector commitments, which is based on curl trees and collision resistant hash functions. In this case, the size of proofs is logarithmic. The last decade, there has been a long line of research describing constructions based on specific number theoretic assumptions, and sometimes with constant size proofs. We also have constructions of rings, and the recent years there has been a number of generalizations of the concept that extend vector commitments with additional functionalities, like functional commitments for linear functions, vector commitments with subvector openings, or proof aggregation. In the paper, we consider a different extension, which is the ability to generate a short proof that a committed vector is small. For example, using two group elements, we can prove that a committed vector is binary. Using three group elements, we can show that a committed vector is a small infinity norm. We can prove the smallness of the Euclidean norm using 6 group elements, and the smallness of the Hamming weight using 4 group elements. We can then give two applications. One of them is a very short range proof. Actually, it's a batch range proof. We can prove multiple ranges at once for the different components of the vector using only 3 group elements. And as a second application, we give a construction of short proof that a ring delivery ciphertext or an FHE ciphertext is valid using only 3 group elements. And without any changing the CRS, we can also prove equalities or inequalities between plaintext, Hamming weight constraints on the plaintext, and things like that. All these constructions rely on the same building block, which is a short proof of binarity. It's based on a commitment scheme that was published in a paper by Moti Young and myself back in 2010. In this construction, there is a two-state setup where you have powers of alpha in the exponent, and one of them is missing. And for security, it should be infeasible to compute the missing element from all available ones. A commitment is essentially a Petersen commitment with the difference that the generators are not independent. They all depend on the same alpha. And when you look at the commitment, it can be seen as a polynomial evaluation for the input alpha. And the coefficients of the polynomial that you commit to is actually is made of the components of the vector. And using the special structure of the CRS, you can open it for one position by revealing only one group element. And it's binding because if the adversary was able to open the commitment in 2 different ways for some position, then he would be able to compute the missing element of the CRS. The construction extends to prove that a committed vector, to prove inner relations between a committed vector X and a public vector Y and a public scalar Z. Using these properties, we build short proofs that the committed vector is binary. So we have a commitment in the second source group of the pairing, and we want to prove that it's a commitment to a binary vector. And to do this, we will prove that for each component xi times xi minus 1 is equal to 0. And we will do it by proving that a random linear combination of these products is actually 0. So the same idea was used in bulletproof, but we want to do it using a constant size proof. So we first hash the commitment C hat to obtain a vector of a random coefficient, which is used to compute this linear combination that should be 0. To prove that it's 0, the prover will create a commitment to the reversed Hadamard product of y and x. So it's a commitment to the component-wise product of y and x, but in the reverse order. Then, since the commitment is additively homomorphic, you can divide this commitment by y, and you obtain a commitment to the left-hand side of this inner product. And then, actually, this is the left-hand side argument of this pairing. And when you compute a pairing of this quotient with the commitment c hat, you compute a product of polynomials in the exponent. And in this product of polynomials, the coefficient of degree n+1 is the inner product that we are interested in. And actually, it should be 0 when the prover is honest and when the vector is binary. So when the prover is honest, he can compute a short group element pi y that satisfies this equation. But it's not enough because the prover has to prove y is consistent with c hat, and that cy was actually computed as the Hadamard product of y and x. So to do this, we can use the aggregation properties of the commitment, exactly as in the point proofs commitment. We can do it using only one group element, which is used to show the consistency of c hat and cy. And this group element can be aggregated with the pi y group element that was used to show the orthogonality property of the previous slides. Eventually, we have a proof of binarity which consists of only two group elements, the auxiliary commitment cy and the aggregated proof pi. We can show that it's knowledge sound in the algebraic group and random oracle model, but we will be able to prove a stronger simulation extractability property when we use it in a range proof. In range proofs, the goal is to show that a committed integer lives in a range of size 2 to the L. The standard approach to do this is to decompose the integer into bits, to commit to each bit individually and prove that each committed value is a bit, and that they recombine to the initial integer. When we in the usual way, we have a proof made of L group elements. It can be reduced to log L using bullet proofs, but it's still not constant. Actually, there is an existing construction of a range proof elements, which is based on polynomial commitments. It was described in a blog post by Bonnet et al. But we can achieve an even shorter proof using the proof of binarity that we described on the last slide. We can obtain a proof which is as short as in the growth 16 snark, and we can also prove it simulation extractable. The idea of the range proof is the following. We have a commitment in the second source group of the pairing, and we want to show that it's a commitment to an integer of size L. To do this, we decompose the integer into bits, and we commit to a vector that contains the binary representation of x. We generate a short proof that it's a binary vector in the first step. In the second step, we prove that when we compute the inner product between this binary vector and the vectors that contains the powers of 2, we obtain the initial integer that was committed to. And we can do it using only one group element, which can be aggregated with the pi component of the proof of binarity. And when we do this, we obtain a proof made of only 3 group elements. We can show that the construction is a simulation extractable in the algebraic group and random oracle model using the 2 n discrete log assumption, which says that alpha is feasible to compute given all these monomials in the exponent. The idea of the proof is that the reduction will be given all these elements, and will simulate the view of the adversary without using g to the alpha to the n+1 at any time. So this element is never used by the simulation. And since we are in the AGM, the adversary's fake proof should not depend on gn+1 either in its algebraic representation, because the adversary has never seen any group element whose algebraic representation depends on this guy. And yet, we can show that if the knowledge extractor fails, the reduction can obtain a different representation of pi star that will depend on gn+1 with high probability. So the reduction will be able to compute two different presentations of pi star, one that depends on gn+1 and one that does not. And this reveals alpha as a root of a non-zero polynomial. To achieve simulation extractability, we also need to build a trapdoor-less simulator, and we do it by programming the random workers as a function of previously chosen aggregation coefficient, which is something that a real adversary cannot do. But we need to distinguish several cases to prove that the adversary cannot recycle an output of the simulator. So if we compare it with earlier constructions that give constant size proofs, the constructions based on growth 16 and polynomial commitments have a faster verifier because the verification time is constant. It does not depend on the length of committed integers. But we have the smallest number of exponentiations at the prover and the smallest proof size. The proof size is the same as in growth 16, but we have a much smaller number of exponentiations at the prover. In growth 16, the number of exponentiations would grow with the size of the circuit that computes the commitment to opening. And also we can construct a batch version of the scheme that proves multiple ranges at once for the different vector components. And as a special case, we have a short proof that the committed vector has a small infinity norm. This brings me to the second application, which is a short proof for lattice statements. Consider the usual power of two cyclotomic ring, and it's a quotient ring for a modulus Q. We consider vectors of ring elements over RQ, and we want to prove that the knowledge of small ring elements that satisfy this linear relation. Many statements in lattice-based crypto can be written like this. For example, if you want to prove the validity of ring enable ciphertext, you can see T as the ciphertext and the AIs as the public key. So this can be done using different approaches like MPC in the head or lattice-based proof systems. Or you can also use shorter constructions based on discrete log related assumptions. You can do it either arcs or a direct approach that was considered by Del Pino, Lyubashevsky, and Zeiler in PKC 19. Their idea was to rewrite the statement over the initial cyclotomic ring and prove it over this ring. They rewrite the relation as a relation between integer polynomials without any reduction mod Q. They write it as a relation like this with a quotient and a remainder. And to prove that it holds in this ring, they will prove that this equality is satisfied mod P for a large P, which is larger than the infinity norm of both members. P is the order of the discrete log group, and it's larger than the ring neighborhood modulus. So what they do is they commit to an extended witness that contains the initial witnesses and the quotient of the division. Then they commit to it using a Peterson commitment, and they prove that all these elements are small using bulletproof. And using bulletproofs, they also prove that this relation is satisfied mod P. So we consider the same approach, but we want to have a constant size proof. And to do this, we rewrite the relation as a relation with binary witnesses. So we decompose the witness into bits, and then we adapt the matrix based on this. And then we prove that the committed witness is a binary vector in the first step. And in the second step, we prove that it satisfies this linear relation. But to do it with a constant size proof, we need to compress this relation into an inner product relation. To do this, we multiply both numbers by a random vector theta, and we prove an inner product relation between a secret vector W tilde and a public vector on the left. And this is something we can do using only one group element using the vector commitment technique. And then we can even aggregate this proof of orthogonality with the proof of binarity to obtain a proof made of only 3 group elements that satisfies a pairing product equation like this. The disadvantage is that with this approach, the verifier has to compute a linear number of exponentiations in the length of the witness, because the verifier computes two multi-exponentiations with n generators. But we can actually, there is a trade-off with only a constant number of exponentiations at the prover. It just doubles the size of the proof and the cost of the prover. The idea is that when you look at these two multi-exponentiations, you can see them as KZG commitments to polynomials that the verifier knows. So we can ask the prover to compute these two commitments, to these two KZG commitments on behalf of the verifier and prove that this is done correctly. It's just an evaluation proof on a random point. So if the prover wants to cheat and send commitments to the wrong polynomials, then he will be caught by a short-zipper with high probability. With this modification, the verifier only computes 8 exponentiations and 4 pairings. The only thing that depends on n is the number of field multiplication, which is 2n, which is much faster than an exponentiation. And if we compare it with a snark, we can compare the cost of proving a ring-able ciphertext in the LPR10 construction using, for example, the Grove 16 snark. If we do it like that, we need a number of R1CS constraints, which is roughly 150,000. And the CRS would be something like 50 megabytes. And the prover would compute over 1 million exponentiations. We can reduce the cost of the size of the CRS by a factor of 2, and we can also significantly reduce the number of exponentiations at the prover. Another advantage is that we can prove other statements like plaintext equalities, like Hamming weight constraints on the plaintext or things like that without any change in the CRS, which is not possible with the snark, at least not this one. Actually, it was implemented by Zama to prove the validity of a ciphertext in construction by Joa to appear in the next CTRSA. We can prove the validity of a ciphertext using vectors of dimension 65,000, using about 4 seconds on a laptop using 12 cores, and verification takes 50 milliseconds on a powerful machine. So it's practical, and it's being integrated in Zama's FHEVM. To summarize, we gave direct constructions of vector commitments with short proofs of smallness to prove the smallness of the Hamming weight, the smallness of the norm, and we gave security proofs in the algebraic group and numerical model. And for the two applications that we described, we can prove simulation acceptability in the algebraic group and a numerical model. And thanks for your attention.
We have time just for a very short question.
Thanks a lot, Tom. And I was wondering, can we mention event group together? I have many values, and can I mention the value for of them?
You want to aggregate proofs?
Yeah.
There must be a way to do it if you combine the snark in a recursive way, but I don't see a more efficient way to do it.
Thanks for the speaker of this session. It's